Great. All right. Well, thank you everyone for joining. So I'm presenting dielectrophoresis as a means for artificial gravity. So I want to acknowledge there have been a lot of students that have supported this work in the Charger Advanced Power and Propulsion Laboratory. We're part of the Propulsion Research Center at the University of Alabama in Huntsville. I wanted to include names because I'm really big on credit. And I'm not perfect with it, but I try to do that. But I wasn't sure about sharing faces and names in a public forum like this. So I'm just acknowledging all the contributions, and we'll just move forward. Whenever I give talks that are related to advanced propulsion, especially publicly, I like to have a little fun and go through some of the very, very basics. Like, for example, units and dimensions. So our time unit is basically defined as 1 second. But what does it actually mean? Like, what's our best definition? So right now, it's a fixed numerical value of cesium frequency. It is the unperturbed ground state hyperfine transition frequency of the cesium atom to be, I believe that's 9.19 gigahertz, where 1 hertz is equal to 1 over 1 second. It used to be defined as a fraction of a day. 1 hour is 3,600 seconds. A day is 24 hours. A Julian year is 365.25 days. To better than 1%, 1 year is approximately pi times 10 to the 7 seconds. So if you want to wow your friends, you can say, hey, a person that's around 32 or 33 is about 1 billion seconds old. So you can just keep that in the back of your mind for parties. I'm sure you'll be very popular. So moving on, the length scale for spacecraft, celestial bodies in the solar system. So a meter is a very useful distance for a spacecraft. So, a spacecraft might be a few tens of meters long. A foot is 0.3048 meters. A kilometer is 1,000 meters, used to describe orbital altitudes and radii of celestial bodies. An astronomical unit, so what is that? That is 1.49 times 10 to the 11 meters. And that's roughly the average distance between the sun and the Earth's orbit. Our solar system is about 100 AU, depending on where you decide the boundary is. The approximate distance from Earth to Sun is 1 AU, as I just mentioned. But really, there's this long, wordy definition that I'm not going to get into, but you can pause and screenshot it if you want to. So this is just definition of length scales. For interstellar distances, there's a couple of length scales that are very useful. The light year, of course, which is I should have put that in scientific notation. Whatever that is in meters. A light year is the distance that light travels in a vacuum in 1 Julian year. So it's about 63,000 astronomical units. Our galaxy is around 100,000 light years across. In 1 nanosecond, light travels just under a foot. So it's about a foot a nanosecond is how fast light speed travels. That's often useful in circuit analysis and pulse power, things like that, understanding how fast a wave travels down the transmission line, for example. A parsec is kind of a funny unit that requires some illustrations unless you're an astronomer to figure out what exactly it means. So a parsec is 648,000 per pi astronomical units. It's about 206,000 astronomical units, or 3.26 light years. It's the distance at which 1 AU subtends an angle of 1 arc second. And since this is a public forum, I'd like to suggest that maybe 12 parsecs be the definition of a parsec and connect that to the Kessel run. That would be my personal preference for a better, proper definition of a parsec. Moving on to velocity, this is a thing that I think that all of us really care about. We want to go fast. We want to get to these destinations quickly. So we have a meter per second. That's the basic SI definition for a velocity. We have mile per hour, which is 0.447 meters per second. If you're trying to do this in your head, take miles per hour, divide by 2. You get kind of close-ish to meters per second. A kilometer a second is a very useful unit of velocity for orbital speeds. So they're easiest to measure in this unit. 1 click is a kilometer per second. It's about Mach 3. 7.5 kilometers per second is LEO, or orbit velocity, about Mach 23. The speed of light is almost 3 times 10 to the 8 meters a second. It's the speed of light in a vacuum, and that's about Mach 1 million. So Mach 1 million is the speed of light, roughly. Now, in science fiction, we have warp speed in Star Trek, and the next generation, all modern content, roughly from 1 to 9, is given as warp to the 10^3 power. The scale from 9 to 9 point, let's say 6 9 is much more complicated. The original series, warp to the 3 power times c was basically what your speed was. And hyperspace, so if we look at Star Wars, is much faster than typical Star Trek warp speeds. It moves as fast as the plot needs, according to script writers. That's based on interviews, I think. And let's say the galaxy has a diameter of 10 to the 5 light years. It'd take a week to cross the galaxy. That gives a little over 5 million times the speed of light. Now, the most important one of these, of course, is ludicrous speed. That is about 1,000 times the speed of light. And this comes from a highly reputable source about Warp 8. And I found it in an article in Reddit. So I'm sure that's peer-reviewed and legitimate. So anyway, that kind of collects typical velocities in science fiction. So moving on, where do we come from and where are we? And when I say we, I'm talking about the group of us at the University of Alabama at Huntsville in the Charger Advanced Power Propulsion Laboratory. So it's a laboratory in an industrial space that's about 8 miles off of campus. I think when they found out we were doing a lot of high voltage stuff that could lead to radiation output, they decided to put us as far away from campus. Actually, the truth is we didn't have space on campus for all the equipment that we had accumulated over time. And so this is the interior of our lab. So it's very condensed because we have a lot of high voltage equipment and pulse power equipment that's kind of compressed in there. We originally were on the Redstone Arsenal in a very large lab space that we were spoiled and had infinite lab space. So we accumulated a lot of things. And then as we had to move over time, we had to kind of condense and economize our space usage. So this is just sort of a collection of some of the things that we have in the lab. Let me go backwards. These are some older power supplies that we've refurbished. This one is a plus minus 70 kilovolt power supply, and this is a plus minus 100 kilovolt power supply. And you can see some pallet racks in the background where we store a variety of equipment. This device over here on the left is a pendulum that we use in order to quantify measurements when we do dielectrophoresis experiments. It's a basically non-electronic method for trying to quantify the forces that we can generate when we have high voltages applied. We have a pretty good collection of different types of power supplies. So I showed you those old barrel type power supplies where we pulled the guts out of the barrel, but we do have some more modern switching type power supplies. These two here, I think it's called Analog Technologies. I don't work for them or anything. I just bought their stuff off of eBay for a pretty good price. These are plus minus 60,000 volts. Then we have a more experimental one, which basically involves a signal generator, a ZVS flyback or flyback driver, flyback transformer, and then a Cockcroft-Walton voltage multiplier, which gets us somewhere between 200 and 400,000 volts. We're in the process of trying to measure it because it's not an instrumented supply; it's highly experimental. This is an AC high voltage power supply from Information Unlimited, and I'm sure a number of you that are hobbyists are very familiar with that website and disheartened that the gentleman that ran it, passed away, I think this past year. So fortunate that we could buy some stuff off of the site before he passed. And then over here, these are some of the typical tools that you need when you do dielectrophoresis. We need to be able to measure high voltage. So these are a couple of voltage dividers. The one on the right measures up to 40,000 volts. The one here is longer, it measures about 100,000. There's an exponential relationship between the voltage rating and the cost of these things. They are sitting on top of an experimental voltage divider, which will allow us to measure up to about 250,000 volts, which a student built that based on a a paper that we found. And so over here, this isn't really related to the talk, but one of the things that we do is pulse power. And this system back there is a 60,000 joule pulse power machine that the students named Sparky. It's generated up to 900,000 amps in a 3 microsecond pulse, and we could push it harder than that. We just haven't done it yet. So anyway, that's some of the equipment that we have in the lab. So even though I'm not talking about propulsion, I'm talking about artificial gravity. We have in mind trying to make space travel easier. And one of the things that's really hard on astronauts is that microgravity environment. But to kind of frame it all, I like to take a look at where we could go, like what are the destinations, and what are the scales involved here. So if we look at this chart here, this is Earth, that little tiny blue dot, and then Leo is this orbit around Earth. And the scale here, the X and Y axes, are length scales of astronomical units. And you can see we're barely scratching the surface of 1 AU, like 1/1000th of an AU, 2/1000ths of an AU, and so on. And out here is lunar orbit. That's as far as humans have gone, period. I mean, we've sent probes much farther than that, of course, but we've never sent humans any farther than this. And this is a tiny, tiny fraction of our own solar system, let alone the galaxy or superclusters of the universe. So you can say, all right, so here we are, and this is our celestial neighborhood just here. This is our backyard, all of these different planets, and this is on an x-axis scale. And basically, this covers 99% of all the space missions. And how come we haven't gone farther? Well, because our crew habitat is really, really difficult. It's hard to survive in deep space, and our propulsion systems just really don't allow us to do much more than this. It's really hard to get off the ground and get into orbit and leave Earth's orbit. A lot of people are excited about interstellar travel or travel to some of the other planets. I personally am really interested in us visiting some of these other smaller worlds, like, for example, some of the larger moons that surround Jupiter and Saturn, or some of the Kuiper Belt objects, or the planet Pluto. I'm never going to get over them downgrading Pluto to a dwarf planet. I like Pluto as a planet, but that's okay. I don't want to get on the soapbox too much there. But anyway, the point being is that there are a lot of really small bodies that have of the order of a few percent gravity of Earth. They're mostly cold and rocky, but there's so many of them that I think it just means there's a lot of different opportunities for habitats, sort of like terrestrial habitats in low gravity environments. There's probably all kinds of different mineral deposits of sorts to really kind of live off the land, if you will. So I hope that we kind of keep a lookout for visiting more and more of these things, because I think expanding in the solar system kind of gives us a really good, healthy foundation for then expanding beyond that and going to the nearest star systems. Another thing I like to do is talk about why we should send humans, say, for example, to Mars, which is kind of like the typical go-to beyond the Earth-Moon system. Is why would we bother to do this? And there's always the inspirational things, but it's kind of like singing to the choir, because a lot of us that watch these types of presentations are all sort of like-minded to begin with. But if you're trying to sell it to a broader audience like taxpayers, there's actual real reasons to do this. So based on numbers of neurons and firing rate, human brains are capable of something of the order of 10 to the 15 to 10 to the 18 flops, floating point operations. And they only require about 20 watts to run. So we don't have computers that can really do that. And that gives us faster speed and higher efficiency. We also have hands, so that we have agility and dexterity to go places that are kind of difficult for robotic access. But I'm not saying that we get rid of robots or we get rid of computers at all. I think that humans bring vision, creativity, intuition, and problem-solving capabilities, while computers and AI tools really can handle the execution, optimization, and data crunching, so that the collaboration really brings about revolutionary capabilities that's just not available without both present in the location that you'd like to explore. Another reason to send people is because the on-site teams overcome the communication lags, because Mars, which is our nearest neighbor, the communication time lag is between 6 and 20 minutes. And so every time you want to interact back and forth, it takes quite a while to, send and receive those communications. So this chart basically summarizes where we can go in the solar system and kind of nearby interesting interstellar destinations. So if you see this little animated GIF, this is something I calculated sometime, I think last week or 2 weeks ago. And this is kind of a fly out of our solar system, where you start from the interstellar system and you sweep out. And those planetary positions, I think, are correct as of a couple of weeks ago, where you start to see Sedna's orbit, and then the Oort cloud, which is entirely made up. That's not necessarily accurate, but just kind of representative of the scale of where the Oort cloud is hypothesized to exist. And then you see a collection of stars, and the ones with the little border around them are the habitable planets that we know of just in our neighborhood. And this is, again, goes out to a radius of 11 and a half parsecs, again, to acknowledge the old Kessel run. But on this chart over here, this kind of shows from rocket propulsion context what we can do. The x-axis is the energy density in the fuel that we can carry. So it's joules per kilogram, chemical. So this gasoline, rocket fuel, all that kind of stuff gives you maybe 10 to the 7 joules per kilogram. And this line corresponds to roughly how fast you can push the gases out the nozzle. And it's the technology that we have at the moment. And so just kind of looking at that, it kind of tells you what's possible. So you look at this intersection with these different horizontal lines to kind of connect what's possible with the technology for the given mission with difficulty going vertically like this. And you can see with chemical, you can do lunar round trips in a week. You start to push the limits in doing Mars round trip in a couple of years. It really helps if you can do refueling so that you don't have to carry all that fuel to the destination and back. But then if you want to do it in 6 months, it gets almost impossible with chemical. I suppose it could be done, maybe, but it gets a lot harder to do this. And then as you start pushing out to, say, a Titan sample return, or a heliopause flyby, or an Oort cloud flyby, gravitational lensing, and so on and so forth, it really starts to get impossible until you start adopting nuclear technologies, or maybe antimatter way out here. And then you can see there's this big gap where, honestly, I don't know what's interesting in between a delta V requirement of 10 to the 3 kilometers per second out to the next star. But then you can kind of get into interstellar journeys. And even then, it's pushing the limits of nuclear technologies, and you kind of need antimatter, or you need breakthrough propulsion, which is why we're all here. So now I want to get into some health risks for humans. Some of these arguments came from someone I researched and actually got to speak with, Dr. Torin Clark, who has researched artificial gravity means using centrifugal methods. And so they've collected a lot of really good arguments about stuff like this. So primary microgravity health risks include things like bone loss, muscle weakening, cardiovascular deconditioning, sensory motor impairment, and ocular damage and vision degradation. So if you're in space for a long time, it can be quite challenging. And they're greatly weakened when they return to Earth, or for future when they land on Mars. So you can imagine sending humans to Mars and they get to the surface and they can't do anything until they go through physical therapy and condition their bodies. I don't know if that's exactly what's going to happen, since Mars has about a third the gravity, but that could be a potential problem. And so you have to do a lot of countermeasures in order to overcome this. So astronaut deconditioning is a threat. And so that's one of the things that we thought that we might be able to address. So what is dielectrophoresis? And why is it relevant here? So Dielectrophoresis is a charge-independent body force that's created by a gradient in electric, DC and AC fields both work, fields. The approximate dielectrophoresis equation, so just qualitatively speaking, is particle volume, some kind of polarizability factor. That's just, think about a molecule, its polarizability, if it's stuck in a solid substance, is how much does it sort of rotate, along the field line. And then you multiply times the gradient in the electric field squared. So there's various ways of calculating and approximating this polarizability factor. And the force is usually, not always, but it's usually in the direction of the gradient. So let's take these pictures here. So you have, let's say, for example, an electrode. This is the red plate, and then you have another plate that's oriented a different way here, so that you've got almost like a sharp point on one side and then a flat side on the other, where you're deliberately creating a gradient in the electric field. So the lines kind of bunch up down here towards this side. And generally speaking, you have an attraction of objects immersed in this field towards this sharp side. Now, you can get a repulsion, but in order to do that, what you have to do is have this in a medium in which the permittivity of the medium is less than the particle itself. No, it's more than the particle itself. I got that backwards. I'm sorry. So dielectrophoresis is a 100-year-old concept. It's used quite a bit in, say, for example, biomedical sciences, particle extraction. We're actually looking at using it for nuclear thermal propulsion, not as the propulsion system itself, but basically to kind of help control. Well, it's been considered for control of propellant sloshing. That's actually one of the original aerospace applications I'm aware of, from someone named Jim Blackman in his dissertation that came out in 1958, I believe. So these are just some kind of typical things that have been done in the area. So Blackman's work, which was published in '65 in an AIAA paper, looked at it to collect liquid propellant. So an idea is to keep the liquid hydrogen propellant for a nuclear propulsion system away from the walls so that it doesn't boil off and leak out. And but you have to basically suck it down to the pump so that you can pump it when you restart your propulsion system. And so he was looking at how you could control that hydrogen and basically draw it to different electrodes and then draw it down to the pump. And there were a number of challenges that he encountered, including arcing and high voltage breakdown. And then there was additional system complexity. And then I think, again, they picked this up again in the 70s to reconsider it, but it didn't really progress beyond those concepts. And then some early experiments that Dr. Blackman did. But let's kind of summarize what we've talked about so far. So the effect of dielectrophoresis is highly dependent on geometry of the electrode setup, applied voltage, dielectric property of objects and in particles in the medium. The force direction depends on the geometry setup and the electrodes to create the field gradient. And it varies strongly with particle size, applied voltage, and dielectric properties of material, tissue, and medium. Now, the picture over here is a picture of Alessandro Volta. We had the pleasure of traveling to a conference, and whenever I'm out in public with my wife, I have a tendency to embarrass her at least once because I sort of forget I'm out in public. And we were in Italy for this conference, and we were up in what's the town, Como. And I saw this statue. I said, "Hey, I'm going to check out who the statue is of." And I walk up and I get closer and I realize, oh, it's Volta. Oh my gosh, he's like the father of everything that we're doing. So I got super excited and started clicking all these pictures and running around and scaring the pigeons. And people are staring at, who's this lunatic, geeking out on this statue over here. So anyway, that was very, very, very recent that we did that. But I also wanted to credit Volta here because he did things like help us develop an understanding of the connection between geometry and charge and voltage. And while he didn't invent high voltage power supplies, he kind of perfected one and kind of made it popular for doing experiments. And so So it just made enormous contributions early on. So moving on. So how do we get into this? So my background is in fusion. Primarily, we've done numerical modeling of fusion for national labs, other universities, small companies. But we started to develop a pulse power laboratory so that we could do some experiments ourselves. And so we kind of got the hang of how to safely manage high voltage. And when the pandemic hit and I had a lot of free time, I was just kind of stumbling around on YouTube and I realized, there's this interesting phenomenon called dielectrophoresis where they test things at hundreds of volts on micro scales to selectively move, say, tissue, biological tissue, or things like that. And I thought, gee, what could we do at 40,000 volts or higher? So I started, I bought a little power supply and started building things just to try to get an intuitive feel for what's possible. So here's an early picture on my ping pong table where we were able to move things. So you see like a marble that's kind of moving around on an aluminum skirt. There's a ping pong ball that eventually I was able to figure out how to actually pick it up. And then over here, I experimented with different things where we tried to prevent arcing. And we were able to just kind of actively pull things towards electrodes and stuff. And I thought, okay, I think there's something to this. Now let's actually try to make it a little bit more professional, not just whatever I could put together in my garage and and build on a ping pong table. So we wrote a little code to allow us to calculate things like electric fields so that we could make some basic calculations. And we built an apparatus out of spare parts. And so these are three pictures of, say, for example, where we have this protractor suspended from a little stand that we built. And the ball here that's being attracted to this electrode in a sequence of pictures is marble. So we were able to, as we quantified it, we were able to create an attractive force for wood, marble, various types of food. I mean, you name it, we tried it. Chicken, avocado, potato chips, glass. Okay, glass is not a food, but you get the point. So we were able to create up to about a third of Earth's gravity with a, say, roughly 50,000 volts. Now, one of the fun things about doing this is learning how to suppress arcing. And the really good commercial insulators are very expensive, like high voltage putty. I'm sure some of you are familiar with high voltage putty. One of our undergraduate students at the time we did these experiments kind of sheepishly approached me and said, you know, I used to use as a kid this stuff that was called Sculpey. It's an art clay. And she goes, do you think that might work? And I said, well, hey, it's worth a shot. I mean, we can set it up and try it. Why not? So she brought some in and it worked beautifully. So here we go, creating things that we can bake and solidify into these structures. So that surface is a metal electrode entombed in art clay of all things. It's a tenth of the cost of commercial products. I'm not saying it's as good as the commercial products, but when you can go to Walmart and buy stuff that can handle 50,000 volts and it only costs you about $5 for a big, 1 pound chunk of it, it's hard to beat that. So we actually use Sculpey all the time to especially do quick and dirty things as we're kind of rough. So if you're tinkering with high voltage, if you've never done it before, don't just go buy a high voltage power supply because there's a lot of safety issues with it. But if you know what you're doing and this is not in your repertoire, go look up Sculpey. It's a great product for this. So the strengths of this, let me just kind of check my time to make sure I'm not eating into some other speaker's time here, but okay, we're good. So the strengths, so we've come up with something that might be a good countermeasure for microgravity, and it might be a key enabler for long duration human space flight. It's not something that we're saying would compete with and replace centrifugal concepts, because I think they both have their merits, but it's definitely something that, for example, you could integrate in a smaller volume. You don't have to rotate the spacecraft. So it might be that it's a niche for certain types of missions, or it could be combined some way with centrifugal systems. But the neat thing about it is that we can dial the voltage up and down and scale at will to condition people for Mars, Earth, etc. Or at least that's the goal. I'm not saying we can do that just yet, but there's kind of a direction and a path to do that. So I'd kind of be remiss if I didn't talk about some of the other body forces that you can get, the effects that you can get out with other electrostatic methods. So there's a concept called electroosmosis, and this one is kind of hard to understand, but basically there is a surface effect when you have a layer in contact with the material. Think of it in an analogous fashion to how a droplet of a liquid on a surface might spread out, or it might wet and create like a little bead on the surface. So there's similar types of effects that can create what's called an electrical double layer. And so if you apply an electric field along that layer, you can pull ions across that layer, but it's a really small volume. So it's not practical for large scale volumetric forces. There's another one called electrophoresis, which is a volume force, but it requires okay, so there's a statement in here about uranium. So we actually at a conference we're talking about how we could pull uranium vapor out of a hydrogen stream for a special NTP system, and I forgot to get rid of that. I apologize for the confusion there. But whatever you're trying to pull, so generalize that statement to requires whatever is in the air or the gas that's in that environment to be partially ionized. So we don't really want to actively ionize humans in order just to create a force on them. I'm not sure that would be very healthy. So it also might be power prohibitive to do that. So finally, dielectrophoresis is a volume force that does not require ionization. It's frequency dependent, and so you might be able to selectively amplify the force for one species. I mean species in terms of atomic species or materials, not humans versus cats or dogs or something. So species in the context of what materials you're trying to work on. And it seems to be, of all of these things, the best candidate if you are using electrostatic or electrodynamic means. Now, there's some challenges and concerns with this. Number one is the health risk to humans, because if you're dealing with high voltage, obviously you have to worry about arcing, ionization, and stuff like that. There are exposure limits for electromagnetic fields that arise from established biological effects that are known. The International Commission on Non-Ionizing Radiation Protection draws up those guidelines, and most of it comes from high voltage line workers and power company workers. Long-term effects, which are implied for levels much lower than limit values, have not been adopted due to lack of scientific evidence. So there are concerns, but one of the main points out of this I'll kind of just get to rather than kind of grinding through all of these different things, are that it's frequency dependent, and where it really starts to become a problem is when you get into microwave frequencies. Because obviously, if you had an AC field and it was at microwave frequencies, you excite the water molecules and you start cooking whatever's in that environment. So we don't want to do that. So anything that we do with AC fields, there's going to be at much, much lower frequencies, say between 0, which is DC, up to about maybe 100,000 hertz. And all that appears to be safe. But again, a lot of testing has to be done. Kids, don't go out and try this at home. And here's just another chart on frequency absorption. But again, the problems really start in the megahertz range, and we're going to be way below that by orders of magnitude when we do our tests. One quick thing about theory, I don't mean to dump a bunch of equations on this audience, but I kind of connected this in a nice way so it kind of flows. So the basic force really is given by an expression like this, 2 pi times object radius. So it doesn't have to be a sphere, but this is an approximation, kind of like saying spherical horses for those engineers out there that understand a reference like that. And then you have a permittivity value here for a material, and then times the real part of what's called the Clausius-Mozatti factor. And then times the square of the electric field. The Clausius-Milzati factor is a factor that connects the relationship between the particle or people immersed in the field and then the medium, that's the M part. And so in this case, it would be air. And so this gives you that relationship so that you can understand whether or not it's an attractive or a repulsion force. Medium doesn't have to be air, but obviously if you're dealing with humans on a spacecraft, it would be. The complex permittivity in this equation is applicable to both the particles and the medium, is given by an expression like this, where I is the imaginary number, epsilon naught is the vacuum permittivity, and epsilon r is the relative permittivity. And that epsilon r, that's the real secret sauce that can make this interesting for a lot of different applications. So what is the relative permittivity? For example, a gas has an expression that's kind of like this. So N is like the number density of the particle. Q is just a constant, that's the charge. Epsilon naught is permittivity of free space. Electron mass is ME. And then you've got these frequencies where omega 0 is the applied frequency and omega is the resonant frequency of the system. No, excuse me, I got these backwards. I'm sorry. Omega is the frequency that you apply, and omega naught is the resonant frequency of the material itself. And there are a lot of different things that could cause that resonant frequency to be different. It depends on the physics of the medium. There's lots of different things that could drive that. Now, one other undocumented effect that's worth mentioning that we've kind of hacked our way into, and I'm just sharing this with all of you, is that metals don't work at all in DP. Anything conductive really doesn't work well, at least that we've found. However, if you have an AC field, for example, and you just half rectify it, just chop off the bottom or the top half. So here's the dashed line. It looks like we can, and we kind of did this through trial and error of trying things, that you can actually create an attractive force for metals as well. So I think there's probably a whole lot more that one could do experimenting with different types of frequencies, maybe, I don't know, just different effects that one could try, not just sine waves, but triangle waves or other things that might bring about different effects. I think we're just scratching the surface on this, and there's a lot that could be explored in this area. And anyway, and that's kind of the end of the talk here. I have a ton of backup slides if people want to talk about fusion at all, but I'm not inviting. I'm just have it there available in case. But basically, the CAP lab has developed expertise in fusion, pulse power, and high voltage. Dielectrophoresis, which is one of the things that we study, has a potential for aerospace applications in voltages of ranges from 10 to 10,000 kilovolts. Like artificial gravity for crewed spaceflight, debris remediation, material separation, and recycling. And so we're focused primarily on training students while developing fusion sources, high voltage, and advanced propulsion for the next generation. So the main intent of our lab is to train students and have them go out and do exciting things and change the world. So with that, I'll stop sharing and yield the floor back to the audience.